NPTEL lecture on earthquake resistant design of foundations. Today it is 31st lecture of this course, and today we are going to talk about dynamic soil interaction. So this is the we are going to start the new module today. So first of all, the lecture title is Introduction to Soil Interaction. Continuing with that, so what you have here, let me share the slide. So we have the 6 modules of this course. One module, that is miscellaneous, is added now. We already covered introduction. Then we also discussed in detail shallow foundations. Pile foundations was the major topic which we have already covered, then well foundations. And today we are going to start the 5th module of the course, that is SSI for deep foundations. SSI stands for soil interaction, and finally we'll discuss miscellaneous once this is over. So when we talk about SSI for deep foundations, these are the different chapters. That is, it will be divided in this module will be divided into 5 chapters. First chapter of this module is Introduction to Soil Interaction, which we are going to discuss today. Then second will be what are the major effects of SSI and methods of analysis. Then we are going to talk about strong ground motion and wave propagation, which is very important for any SSI analysis to understand. Then we are also going to talk about ground response analysis. And finally, we are going to discuss what is called soil pile interaction. So today, we are going to talk about the introduction to SSI. When we talk about introduction to SSI, today's lecture will be covered under the following heads. First of all, let's discuss what are the damage due to SSI in past earthquakes. Then we are going to talk about basic objective of SSI. Then we are going to discuss importance of SSI and what are the different steps for soil interaction, which is free field motion, kinematic interaction, and inertial interaction. Okay. So these are the coverage here. But before we talk about that, one thing is important, that what is SSI itself. Though term soil interaction, it looks that very complicated. But basically, what happens when the your structures are, like for example buildings, they are situated on the soft soil or on the loose soil, then during the earthquake or during the shaking, the response of the structure is very much changed due to the response of the soil. So basically, as in SSI, the response of the soil will also change the response of the structure. At the same time, how the structure is responding to for a given load, that will also influence the response of the soil. So with that, we continue with that. So let's discuss what are the damages in the past earthquakes. Some of the slides here has been already discussed from some other observation. For example, this is the first slide, which is from 1964 Niigata, Japan earthquakes. And what you could see in this slide, it shows the liquefaction-induced bearing capacity failures to piles. So what can be observed here, that you have a number of buildings, okay, and these are the tall buildings, and most of the buildings are standing, but few are got damaged. So for example, these 2 buildings get tilted, while this building is almost uprooted from the foundation. It appears that its superstructure is all right, but there is a what is called foundation failure here, and that foundation failure is here, right? So when you have this here at this point, so for this building, and why this foundation of this building get failed, because due to the liquefaction below, that bearing capacity of the soil get reduced, and it is not able to support the foundation, and it gets failed. Here, when we talk about liquefaction, this is also the effect of soil amplification, which is the first step of SSI, and that we'll discuss in detail, very much detail, when we discuss later. Continue with this. This was one of the examples. Other two examples where there was a damage of bridges in past earthquakes. Again, it is soil amplification as well as liquefiable soils. These, of course, these slides we also discuss when we discuss the pile foundation passing through the liquefiable soils. So this photograph, first one is from Kobe earthquake, 1995 Kobe earthquake, while the second one is 1964 Niigata earthquake. The first is for Nishiomiya bridge, which got damaged, where softening of pile foundation occur during Kobe earthquakes, and the downward is the Showa bridge, where with its one span get flattened due to the ground. What you could see here, the deck of the bridge fall down, and this is basically due to foundation failure. Same thing happens in case of the Showa bridge. You could see once the simply supported span collapsed, then the deck of the bridge get fall down. Here, one thing you need to understand, in all these cases, there are issues related to liquefaction, but at the same time, there are issues related to soil amplification also. Continue with that. This is a classical example of soil amplification, or what we would say that the effect of SSI on Hansin Expressway bridge due to in Kobe earthquake. What you could see clearly the deck of the bridge is here, passing it appears to be intact, and here there are damages to piers, and there's this piers that fall down. As a result, deck is also fall down. So in this bridge, there is a failure to the piers, and it is again related to the soil amplification effect. Continue with that. Then you have another example here, which is Higashi-Nara viaduct collapse, again from 1995 Kobe earthquake. So what you could see in this case, that you could see the reinforcement is visible clearly, and that means this cover is totally exposed, and this is also a failure due to the soil amplification, ground amplification, which we are going to discuss in one of the lectures during this module. What you could see that once this the piers fell down naturally, that this bridge is going to be collapsed. So it happened in 1994 Kobe earthquake. Now there is another example which is also from Kobe earthquakes, and this I think we have discussed when we talk about liquefaction. So this is a typical example where it is said that when your structure are situated on the pile foundations or deep foundations, they get survived. So the tank was situated on the pile foundations. Piles was passing through the liquefiable soils. Soil get liquefied. As a result, due to soil liquefaction and ground amplification, there is some damage to piles which could be visible here. It could be seen easily here. So if we see here, this is you could see some damage to piles, but at the same time, this tank or the superstructure remain intact. So there are small damage to only small cracking of plaster and other things for piles, but they are safe, they are working. But there was no damage to the superstructures. So that means this pile foundation, due to this pile foundation, this structure survived. Continue with that. This is another example of soil amplification, but this example is from 2001, January 2001, Bhuj earthquake of our country. You could see that clearly there is a peculiar damage to pier cap of the bridge, and this is again this amplification effect. Once this is this waves got amplified, and this pier cap got damaged. Now what happens when this, due to this soil amplification or liquefaction, typical examples, what happens to the piles when they are passing through the liquefiable and non-liquefiable zones. So these kind of things we discuss when we discuss the piles and liquefiable zones, and again we are discussing here. As mentioned earlier, let's say that this is, you have the piles, on the top of it you have pile cap, and on the top of it you have the piers. This load is applied in the horizontal direction, in vertical direction, as well as rotational. That is what we call the moment on the pile cap. And once these loads are applied on here, then what we may have here, that because there is a junction between non-liquefiable zones and liquefiable zones, as a result, more stresses will come at this junction. You could see that pile got buckled here, okay? And there is a deflection. If I say this was the center line of the pile initially, but now the center line of the pile is moved to here, the dotted line. So much deflection occurs due to this liquefaction, and which could be possible due to this ground amplification or soil amplification. So these are some of the examples and where this damages are. Now let's talk about what is the basic objective of SSI, or soil interaction, and how it works, and what is the meaning of SSI. So we will discuss, that its importance, but before that, what is the situation when you have static loading and when you have the dynamic loading or seismic loading. You could see in this figure, a structure is situated on the soil layer, and it is what is called layered system. We have a number of soil layers, and these soil layers are on what is called half space. Okay. When we say structure here, this structure include foundation also. So this include the foundation also. So this is including foundation. Foundation, because for foundation you know all the things, you know the dimension, you know the material. So here the foundation is assumed to be the part of the structure itself. There is no separate. Okay. So this is plus foundation. Now what you have, this structure including its foundation is subjected to what is called if suppose you have subjected to static load only, and then structure is situated on soil, not on the rock, then what we can do, we can consider some part of the soil with the structure and analyze. So here the problem is due to the unbounded domain, because compared to the structure, one of the major issue in the soil is that Mother Earth is an unbounded domain. It is not a fixed domain. So we need to consider the unbounded domain, and how we can consider this unbounded domain while analyzing for static loading as well as dynamic loading. For static loading, what one can do, one can consider some part of the soil with structure and apply what is called a fixous boundary. Fixous boundary is such a boundary which is not really there, but you are considering some part of the soil with judgment with the structure, and then you can analyze the soil with the structure, and this analysis is all right. There is no problem for static loading. But when you deal with the what is called the seismic loading or earthquake loading, this kind of analysis is not permitted. And what is the reason for it? Because when this structure is subjected to seismic loads, then the waves will vibrate. Okay, and structure will radiate some vibration will come from the structure. This is, let's say, seismic loading which is applied at the base of the structure, or let's say directly on the top of the structure, which may be external dynamic loading, which could be due to machinery loading or some other reason, for example wind loading, whatever may be the reason. So in general, when this structure is subjected to what is called the when the structure is subjected to vibrations, then how we can deal with that. So let me erase this one. Okay, so when this structure is subjected to seismic excitation, then waves will travel from structure and they will hit this fixed boundary. If this boundary would not be there, then in that case, these waves will continue to travel to infinity and it will not come back to the structure. But once you place this boundary at some depth below the structure, then this boundary will reflect some waves, some part of the wave, this wave back to the structure, though some part is maybe already, maybe still continue to go. So that means, and if this boundary would not be there, then this would have been gone after this boundary, after this, and this would have continued to infinity. This will not reflected back to the structure. So due to the presence of this boundary, this reflection which is shown in dotted line is occurs, and that is not permitted. So this is a reflection R. Okay, and this reflection is not permitted. Why this is not permitted? Because you are putting this artificial boundary or fixed boundary. In fact, there is no boundary. This boundary has been put here to simplify the problem. And this kind of simplification is all right for static loading. But when you deal with the seismic loading or dynamic loading, then this is not permitted. Okay, then what one need to do? One need to design this boundary, fixed boundary, in such a way that this boundary act like an energy sink. Energy sink, let me write here, this boundary act like an energy sink. Energy sink. Energy, difficult to write with this. So energy sink. That means all the incoming waves which hit this boundary should be absorbed by this boundary and no wave should be reflected back to the structure. And if you say that all incoming waves are absorbed with this boundary, no reflection, that satisfies that condition. So that condition is called radiation condition. So the boundary should be modeled in such a way that it is able to model the unbounded domain, and that should be done using what is called the satisfying the radiation condition. So that means radiation condition need to be satisfied in any case, and this is the basic objective of any SSI analysis. So again, I summarize it here. For soil interaction, it is important to model the unbounded soil domain, and this unbounded soil domain should be modeled in such a way, if you apply a fixed boundary, then this boundary should act like an energy sink where all incoming waves get trapped inside this boundary, but all the outgoing waves are stopped. So this boundary will be acting like an absorber. Okay, so once this is done, that means you are able to simulate this boundary perfectly. And there are different choices to model this boundary, which we'll discuss later. Here, one thing is there. If you have a rigorous boundary, which comes after so much computation, that boundary may be very sophisticated and advanced boundary, which can be used to define this fixed boundary, but that the calculation will be rigorous, and which we are not going to discuss. Rather, we will discuss some simplified way to how to deal or how to model this boundary later. Continue with that. Now let's discuss what is the importance of SSI. So when we talk about importance of SSI, you have two different sides. Okay. And what you could see in this figure, you could see that there are two identical structures. Structures are exactly same, In the first case, the structure, when we say structure, that means including its foundation. In the first case, structure is situated on hard rock, while in the second case, this structure is situated on the soil, and which is a flexible soil. So what you have, let's compare the seismic response of structures which are founded on rocky site and on soft soil site. So here you have rock site and here you have soft soil site. When the structure is situated on the rock, then let's see what happens. But here, before we proceed further, you need to understand that both the structures are identical. That means their material and geometrical property are same, number one. They are subjected to same input motion or seismic excitation applied to the both the structure is same. Here, when we talk about seismic excitation, you could see that there is a vertical propagating waves. As the bigger arrow shows you, this bigger arrow shows you the direction of wave propagation, and this smaller arrow is direction of particle motion. And direction of particle motion is perpendicular to direction of wave propagation. So one can easily see that what is the input wave. So in this case of input wave, the direction of particle motion will give you, this is the direction of particle motion, and size of this arrow for particle motion is telling the amplitude of this particle motion or displacement. So this much is the amplitude. If you increase the size of this arrow, that means displacement is large. If you decrease, then it is smaller. So this the size is also some meaning. Now when this both sides, both buildings are same in both the cases, but one is situated on the rock, another is on the soil. So in both the cases, now let's say that what happens when they are subjected to the loading mentioned here. Okay, so first thing, let's discuss the case when your structure is situated on the rock. It is here. For the structure which are founded on rock, the horizontal motion can be applied directly to the base of the structure. That means you can apply directly to the base of the structure. The input acceleration resulting in the applied horizontal inertial load will be constant over the height of the structure. So first of all, when your structure is situated on the rock, then this input motion coming from seismographs, or let's say for some instrumentation, then it can be directly applied to the base of the structure. Okay, and once you do this, whatever acceleration, applied horizontal acceleration, will be constant over the height of the structure. You could see in this case, even at the height of the structure, you have these two arrows, and the size of both arrows is more or less same, and that means this acceleration, this was the input motion, and output coming on the structure, what you have in this case is constant. Okay, so here continue this. So the horizontal motion can be applied directly to the base of the structure. The input acceleration resulting in the applied horizontal initial loads will be constant over the height of the structure. During the earthquake, an overturning moment and a transverse shear acting at base will develop. And as the rock is very steep, these two stress resultant will not lead to any additional deformation at the base. So when it is subjected to shaking, then you may have some motion at the ground, one overturning moment and a transverse shear component, but this will not cause to any stress, because here it is assumed that your the structure is situated on the hard rock, on ridge. The resulting horizontal displacement of the base is thus equal to the control motion. No rocking motion arrives at the base. So whatever at the base you apply, which is same as your input control motion, and rocking component is neglected here. For a given control motion, the seismic response of the structure depends only on the properties of the structure. So this is very important. For the case 1, when your structure is situated on the rock, then the response of the structure depends only on the material properties of the structure, not on the properties of the rock. So when it is on the hard strata or on the bedrock, then things are easy. But always this may not be the case that your structure is always situated on the rock. There could be a situation when your structure, including the foundation, is situated on a soil column. Below soil column, you have a bedrock, which was the case here. Now, in this case, what happens when the structure is situated on the soft soil? Here, the motion of the base of the structure in point O will be different from the control motion in the control point A because of the coupling of the structure soil system. So, what is A at point A? At point A, control motion is applied here. So, what you have? You have one control motion which is shown in this figure, and you have a control point which is at point A. So the control motion is applied in control point A, which was the case in case of a rocky site, but now the same motion is applied at point O. So when you apply at the point O, then this motion applied to the point O will be different than what was applied to point A, and this was due to the presence of the soil column, which tried to amplify the vertical motions or displacements when it is, so that we are going to discuss in detail. So what is done here, because of the coupling of the structure soil system, the soil affects the dynamic response of the structure in three ways. How it is affected? It modifies the free field motion, and the free field motion is the motion at the site in the absence of the structure and of any excavation. If there were no soil on top of the rock in point C of figure 2C, if you see here, let's see, you have the case here. So what is the situation in this case? Here, the seismic response of structure founded on soft soil is discussed, and there are different figures here. Figure B is outcropping rock. That means on the top of it, you don't have any soil column. In that case, whatever the motion applied at point C will be control motion, and this is point C can be treated as a controlling point. So in this case, the control motion is applied at a controlling point, and its amplitude is shown in this figure, which is the size of the arrow. What happens if you put on this bedrock, on the top of it, if you put or place soil column, then due to the presence of the soil column, not only other points, but at point C itself, that response is changed, and most of the time it will get decreased. Okay. Then if you go the dotted lines are showing you the location of the foundation, where the latter, when the structure is constructed, then foundation is placed at point D and E. Let's consider 2 point D and E. So at point D and E, the motion is get amplified due to the presence of the soft soil column. And as we mentioned earlier, the size of these arrows are telling you the size of amplification. So this here, so this size of this arrow is simply telling you the amplitude. So you could see that at point C, that motion got decreased, but point D and E, it get amplified much. Okay, and this amplification can be observed by comparing the size of the arrow here and another arrow here, which is even bigger than this. That means this due to the presence of soil column, it get amplified. But the motion get amplified, and so this is here. All right. This was the case when you put only soil column. But what happens in the next step? In the next step, you put your foundation at the location of the point D and E, for which you determine the response first earlier. So what you have, once you insert the foundation, base of the foundation, including structure, which is shown here using dotted line, not the solid line, because here only inertial, only the kind of that what is called the elastic properties of the soil is considered, but no mass is considered, and this kind of is called kinematic interaction, or so this will be, that means kinematic interaction. For kinematic interaction, one of the condition is here, that the value, let me write out down here. So for this, inertia need to be 0, so you have mass equal to 0. So that means in this step, the structure is analyzed, this SSI system is analyzed using that there is no mass, no inertia, no inertial forces. So it is free field motion in the C and D, it is kinematic interaction. Now, if you put real structure with some stiffness properties, then whatever the response of this comes, that is called inertial interaction. And what is the difference between these three categories? One is like bedrock here, rock outcropping motion. Then you have free field response, which is different at point D and E with your input motion. Then the same input motion D and E is applied to the base of this, so at the junction here. So then what is seen that you are applying only one component, but which is translating component, but in the result you not only get the translation, but there is a rocking component also. Okay, and finally, when this due to the presence of this rotation and translation, you have at the base of the structure, you have displacement as well as rotation. So this is the effect of inertial interaction. Continue with that. So what we were discussing for the structure founded on soft soil, I think most of the things I have already explained to you. Excavating and inserting the ridge base, say foundation to the site, will modify the rocking component, and this ridge body motion will result in accelerations. This is leading to inertial loads, which will vary over the height of the structure. In contrast to the applied acceleration in the case of a structure founded on rock, this kind of interaction between soil and base in the absence of the superstructure is called kinematic interaction. So kinematic interaction is that interaction which is which can be done assuming that mass of the structure is 0 or negligible. So this when you don't consider the mass of the structure, then inertial forces will not come in picture. Now continue with that. In the presence of structure, the inertial loads will apply to the structure will lead to an overturning moment and a transverse shear acting at point O. This will cause deformation in the soil and then once again modify the motion at the base. This part of analysis is referred as inertial interaction. So what is done here? You have, in case of kinematic interaction, you have your input was only reciprocating component, but you got rocking also in case of kinematic interaction. And again, this the amplitude is inputted at the point O, and this is the rocking component, so that is also coming here. So now due to even your input motion was only reciprocating motion, but here finally due to the presence of inertial interaction, then you have this is applied to the base of the structure at point O, and at point O not only you have the translation, then again you have some rocking component. So this is the change here. Continue with this. Now what you have here, this we have already discussed in detail very much. Then let's summarize the seismic effects of presence of soft soil, which is caused the SSI. What is you call the control motion in the control point, so which could be the point A on the surface, or it could be on the top of some half space. So this control motion, when it is subjected to effect of soil, then what is called, you got modified free field motion. So modified free field motion is obtained. Then once you insert the base inside that, so for example, effect of base, for example, without foundation, in that case, effect of base will increase, and it will lead to what is called kinematic interaction. So in this case, kinematic interaction, you neglect the mass of the structure as well as foundation which is incited to the soil is neglected. So that means we can avoid the inertial forces. But once it is done during kinematic interaction, so your results of kinematic interactions are fed to the next part, that is effect of the structure. And in this case, when kinematic interaction is applied to the effect of a structure, then it leads to what is called inertial interaction. And this completes. So you have this control motion, and on the top of control motion, you have what is called modified free fluid motion. Then effect of base will lead to the kinematic interaction, and finally, when you insert the structure, then it will lead to inertial interaction. Okay, so this was all about it, and this is the reference from which most of the things have been borrowed. A book by Wolf J.P. And the title is Dynamic Soil Interaction, published by Prentice Hall Incorporation, as Eaglewood Cliffs, New Jersey, USA. This is the fundamental book, and this is appeared to be almost 35 years now, but still it is popular in the sense because fundamental concepts are given in this book. So I'll request that please download this copy of this book and start reading that. Thank you very much.